you to the 41st lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. I'm happy to introduce today's speaker, Professor Manish Dev Shrimali, to you. Professor Shrimali did his PhD under the guidance of Professor Ram Ramasamy, who is one of the pioneers who started nonlinear dynamics research in India. After finishing PhD, Professor Shrimali spent a year in Japan and came back to India to work here. He started his career as an assistant professor in the LNM Institute of Technology, Jaipur, and then moved to Indian Institute of Technology, Jodhpur. He joined as an associate professor in the Central University of Rajasthan in the year 2014 and promoted as professor in the year 2015. His current interests are physics of complex systems and machine learning. He had guided 6 students and published around 75 papers. I met him first time in his university when he invited me to deliver a series of lectures on integrability in SERC School on Nonlinear Dynamics. Professor Shrimali gave a very warm accommodation and took us to show some touristic places in and around Ajmer. A couple of years ago, he organized a conference in nonlinear dynamics in his university, and I have been invited for that conference also, but I was not able to attend that meeting. Besides these 2 meetings, I used to attend his lectures both offline and online in recent years. The last one which I heard his lecture is which he gave in ICTS Bangalore. It was a wonderful talk on machine learning. When I wrote to him to deliver a lecture in this series, he immediately accepted. I thank for his support to run this forum. With this short introduction, now I invite Professor Shrimali to deliver his lecture. Over to you, Professor.
Thank you, Professor Senthilvanan, for nice introduction and giving me this opportunity. And before I start, I would like to thank him and his team at Bharathidasan University. And I would also like to thank Professor Lakshman for taking this initiative and bringing all of us to at this stage in the nonlinear dynamics. And he's also here today. So I'm happy to see him here and other audience also. And this lecture series, I'm very sure that is very helpful for the students. And I'll be talking today about this effect of the intermittent and interaction and intermittent noise. So before I start, I'll just make it the full screen and yeah. So is that okay now?
No, we are not seeing your screen. Oh, yes, it has come back.
I think so.
Yes, it has come to full mode, full screen. Yes.
Still there or gone?
No, it has gone.
Yeah. So yeah.
It has come back.
Yeah. Perfect. So I'll be talking about the effect of intermittent interaction and noise. And before I move to that topic, I would like to acknowledge my current PhD student Imelda and recent graduate student Shiva, those who have worked mainly on these problems, and my collaborators Anshul, Shantan, Suresh, Sudhanshu, Paul, Avdesh, Devakar, Sudeshna, Tamil Maran, and Jurgen Cruz for their support and participation in this activity on the intermittent noise and the interaction. And I would also like to thank Department of Science and Technology for supporting my research. Yeah. So The outline of my talk is, first I will briefly introduce the interaction and the emergent patterns because of interaction. My focus is mainly twofold in today's talk, that is the intermittent interaction and the intermittent noise. And I'll tell you what I mean by the intermittent interaction and intermittent noise in short while. So before that, most of the time when we study the dynamical system, the interaction is considered to be a continuous or constant. And whenever the noise also we consider the noise also in a particular distribution. And it is considered to be present all time, all around. So here, if you look at the dynamical systems, most of the time we see that they cannot be considered as isolated units. So they have to have an interaction with the surrounding units. And one can represent the coupled dynamical system with a set of first order differential equations with the function f of x, which represent the internal dynamics of the system. And then you have a coupling function g, and with the coupling strength epsilon here. This interaction can be of very different form, and because of the interaction, the system goes to a certain collective states. One of the collective phenomena because of the interaction is the synchronization, which is the transition from incoherence to the coherence state. And the examples are like coupled pendula, clapping of audience, flashing of fireflies, and so on. One can read more on this by the book Synchronization by Urban Cruz, and there are a lot of review papers and the research papers in the literature. One of the emergent pattern because of the interaction is the coexistence of coherent and incoherent states. So these are the examples from the living creatures, and from the models we can see that if you have a phase oscillator, we can see that some of the oscillators are in phase, and some oscillators are oscillating with the random phases. So there can be a distribution of phase, and we can classify them into the chimera states, and these are the examples from one-dimensional, two-dimensional, and three-dimensional systems. One of the recent phenomena observed due to interaction is the quenching of oscillations, where the oscillatory system goes to the no oscillation state due to interaction, and the oscillations are suppressed because of various regions. And this can be classified into the two categories. One is amplitude death and another is the oscillation death. In the case of amplitude death, system stabilizes to the unstable fixed point of the system due to the interaction. And in the case of oscillation death, system goes to the newly created equilibrium points due to the interaction. And there are certain review articles published on this, which is good for the students. Now, as I told that I'll be talking about this intermittent interaction, where the interaction is not continuous. It is changing with the time or in the space. So very early observation of this dynamic interaction was by Konishi in 2003, where he has introduced this additional coupling variable Z in this limit cycle oscillators given by these two equations, where Z is also changing with time, and because of that, as soon as you switch on the coupling, system goes to the steady state. Later in 2013, Avdesh Prasad also studied the similar phenomena going from oscillatory state to the steady state, where the interaction function is given by ht xk minus xj, where then h is a function of time t, And you can see that the strength of this, the interaction matrix H depends upon your time. So if you consider there's a tau as a time interval where the interaction is with a particular strength A, and from tau to capital T, it is with the strength B, where capital T is the time interval. After that, the same phenomena is repeated. So A and B you can consider to be 1 and 0. If you consider it to be 1 and 0, it can be considered as a switching on and off interaction, or you can consider between any value between 0 and 1. So when you consider this switching on and off type of interaction, and by varying this tau, you can see that the system initially is in the oscillating state, and with the increase of the coupling strength, it goes to the steady state. And similarly, you can do it in the another parameter space. This was also experimentally verified later. And recently, the time varying competitive interaction was also introduced, where the system has a two form of interaction. One is this delta x2 minus x1, and another is y2 minus x1. This is the interaction between the similar variables, and here you can see that the interaction between the dissimilar variables. And again, you can put this delta function as the binary function 1 and b can be or 0 or any number between 0 and 1. So in that case, you can see that I have plotted this the amplitude of the oscillator, first oscillator. It goes from 1 to slowly 0, which is the no oscillation state, and then it continues there, and then with the further increase of the coupling strength, there is a revival of oscillations also. The same, this competitive interaction was also considered in the two different forms of attractive and repulsive interaction, where this G function is considered as a plus minus xk minus xj, and the sign will depend upon whether you have attractive or repulsive interaction. This also leads to the complete synchronization of oscillations to amplitude depth, and then with the very strong coupling, there are the small synchronized oscillations. In the beginning, you can see that for the tau values between 0 to 0.5, you have a asymmetric anti-synchronization state, and from 0.5 to 1, it is a complete synchronization state. That will depend upon whether you have a dominating attractive interaction or repulsive interaction. Later, this time varying interaction was also considered for the system which are in a close proximity. That means that we define the threshold R, which is the range of the interaction, and that will decide the parameter P, whether you are in the interaction range or outside the interaction range, and that will give rise to the time varying Laplacian function G. And you can see that if you look at the such kind of systems, you can observe the synchronization with the change of the coupling strength, and this was done by Devakar and other people, and they have recently published the physics report in 2022 on time varying interactions. So this is all about the initial work on this time varying interaction. And you can see that whenever you consider the interaction which is time dependent, there can be two different ways it can be considered. One is switching on and off of interaction, or going from one form to another form of interaction. Now I will focus on the state space dependent intermittent interaction. And what I mean by the state space dependent interaction is that if we consider the example of the Rosler oscillator, and if I put like some shaded region here, which is, I call that this is an interaction active region. So as long as the state variable of this dynamical system is within the shaded region, which I say that it is a if I consider that as the interaction on region, so the interaction function will take the value 1. If I'm outside that, it will be 0. And I have considered this drive response system here. So you can see that when this there is no state space dependent interaction. So that means that if I remove this xi function here, there is a normal drive response system, and because of the interaction, this system goes to infinity. So it becomes unbounded, and this was the first introduced in 2015 by Sagar Chakravarti and all, that if we control this interaction only in a certain state space, then we can achieve the synchronization, which was otherwise not possible, and system was going to be unbounded. Then later it was also studied further in detail with the function h introduced here, which is a function of the state space x bar. So what we do is we have considered the mean field of the oscillators. So there are n number of oscillators there. We calculate the mean field of the oscillator, which is x bar, and as long as x bar is a certain region of subspace of the state space, then your interaction is active, otherwise it is inactive. So we define the range as we define the normalized range. So what we do is we consider the entire the width of the attractor as the active region with the normalized value delta 1, and we can reduce it to 0 by switching off the interaction completely. So we call it the state space dependent interaction, because here the interaction not depend upon the time, or it is not constant. It depends what the average state space variable of the system, and if it is in a certain subset or subspace, then only there is an interaction, otherwise there is no interaction. So for that, first we have considered the example of Stewart-Lambda oscillator, and there is a coupling function here, epsilon h x bar minus xi, and the interaction is in the x variable of the oscillators, and the frequency is considered to be 2 here. So here I would like to first briefly tell you about the mechanism, how it is working. So I have plotted the two figures. If you look at the left hand side figure, you have this delta equal to 0.4. That means the 40% of the state space is the interaction active region, and 60% state space is the inactive region. And as we have considered the interaction, this function h, which is state space dependent function, that is multiplied with the mean field. When h is 1, it is the mean field interaction, and when h is 0, it is the negative feedback which is given to the system. So now, when you have a 40% state space, there is an interaction is active. So depending upon the initial conditions from where you start, the two oscillators or n number of oscillators will start interacting as soon as they are in this shaded region. And once they leave this region, the interaction is off, and in that case you have the negative feedback that will suppress the oscillations. And now by the time you reach to the boundary, if you have a sufficient energy or the velocity to move forward, you will enter into the interaction active region, and you will try to revive maintain the velocity. So you will see that in certain cases, because the interaction off region is large as compared to the the active region, and the unstable fixed point lies inside that. In some cases, you will land to this unstable fixed point, and there is no more oscillations. In some cases, you will be able to maintain the oscillations. So system will develop the bistability depending upon your initial conditions. Now, when you increase the interaction active region, say 80% of that, then in most of the cases, you will be able to maintain the oscillations, even though there are some distorted oscillations. So here on the top panel, you can see that it is the parameter space, epsilon and delta. Delta is delta you can consider as the interaction active region from 0 to 1 normalized. If delta equal to 1, then in the entire state space, interaction is on. When delta equal to 0, there is no interaction at all. And when it is 0.5, in the 50% state space, there is an interaction, and the rest of the space, there is no interaction. And you can see that there are variety of emergent collective behaviors are observed. Mostly you can see that for the delta greater than 0.5, it is all complete synchronization state, but for the less than 0.5, you have a bistable state, which is a mix of the synchronized oscillations and the steady state, and then it goes to the amplitude end. For higher coupling strength, it goes to the oscillation band. In the middle panel, the amplitude of the one of the oscillators plotted. You can see that this amplitude bifurcates. So basically, the basin is bifurcated into the two regions with the small and large oscillations. And one of the that oscillation goes to the death state at epsilon equal to 2, and the other continues, and then there is a sudden drop. And you can see that there is the bistability region in this case. And these are the examples where you have the unsynchronized and the synchronized mixed oscillations are there, and the oscillatory and steady states are there together. And we have also done this for the time dependent. So instead of state space, what you can do is you can consider that the time interval where interaction is on and off, and it is a periodic in time. So here you can also do some analytical study by taking the average eigenvalue for this the two regions. And you can see that this in the temporal dynamic interaction, you will see that system going from complete synchronization to AD by this continuous second order transition and then OD. So instead of the first order transition, which was observed in the spatial interaction, in temporal interaction, it is not there. Now, what we have done is we have further done some analysis on the average interaction time spent by the oscillator in the spatial dynamic interaction. So what we have done is, since in the spatial dynamic interaction, the interaction is on and off depending upon your status of the system. So what was done, that we have calculated the time when the interaction is on, and average time is plotted in this case. So you can see that average time goes from some non-zero value to 0 as soon as system goes to the dead state, because in a death state there is no time spent in the oscillator state. And we have also plotted this the amplitude of the oscillations, and the analytical value of the transition observed from the time varying interaction, and this matches with our critical transition point with the average interaction time of SDI and the analytical value of this temporal interaction. We have also, because there is a first order transition observed in this spatial interaction, so we have further studied this transition to explosive death, which is a first order phase transition from oscillator to steady state. in a adiabatic manner. So here, this is one example of this second order transition where the y-axis, the amplitude of the oscillator is plotted as a function of the coupling strength, and you can see that it is continuously going to 0, and on the other side there is a sudden jump and there is a hysteresis loop is observed near the transition region. So for that we have considered the van der Pol oscillator, and with the same the spatial dynamic interaction function H. So I will not go into the detail, but you can see that you can observe this first order transition from oscillator to the OD state, in this case, in this parameter space. So I'll conclude here with the first part of my talk, that this intermittent interaction leads to the first order transition in the dynamical system. This can be from first order transition to the synchronization state or to the steady state, depending upon the type of interaction we have considered in the system. So should I take a pause here to take some questions or continue?
Yeah, you can continue.
Okay.
I think. So anyhow, let's Sylvia. So if you have some questions, please rise. Students. Okay, we will continue, sir.
Yeah.
And we will see.
So we have seen that this is the new phenomena observed in the intermittent interaction as compared to the interaction studied in literature in last so many years, where most of the time either you are getting the synchronous or chimera states and etc. But
Manish,
here sometimes, yeah.
Manish, one moment. Just I want to get it clarified. So you say when you have intermittent interaction, you have first order transition, and when this intermittent interaction is continuous, you say it will be second order transition. What is it?
Yeah. So here, not necessarily the way I'm understanding your question is, intermittent interaction will definitely give the first order, but it does not mean that if it is continuous, then you have a second order.
So when, I mean, in the standard or the usual cases, when the interaction is continuous, you get all kinds of collective dynamical states, and
Yes.
so introduction of this intermittent interaction, it leads to this explosive death, for example, in this case. Is that the new feature?
Yeah. So I'll correct here. So this explosive death can also be obtained without intermittent interaction.
Okay.
So yeah. So first thing is with the continuous interaction, you can observe all different kind of transitions.
Collective
First order,
yes.
second order. Now
Yes.
the intermittent interaction, what is new here is the first is the nature of interaction, that we are considering as a state space dependent interaction first time, which was not considered in the past. Second is that in the state space dependent interaction, we will observe the first order transition, not the second order. And this bistability, the first order transition through this bistable region is because of the divide in the state space.
Okay. Okay, please go ahead. Yeah.
Thank you. So the second part of my talk is again related to the intermittent dynamics, but here there is no interaction in the system. So they are independent oscillators, and in the literature, people have studied this the noise-induced synchronization in the identical oscillators. So we can consider, say, two identical oscillators with the dynamic equation as x dot equal to f of x. And when we look at the synchronization, we don't observe the synchronized state in the absence of interaction. When we consider the common noise, like for example Gaussian white noise, can we observe the synchronization? Yes, it was observed in literature that if we consider the identical oscillators, uncoupled identical oscillators in the presence of noise, they go to the synchronization state. And this is the example of Lorentz system. So when you look at the average synchronization error, you can see that with the strength of the noise, it goes to 0, and there's a critical noise strength where you observe the synchronization. Now, there's another quantity called the Basin stability. That is like how many initial conditions are leading to the synchronized state. It's called the stability of the basin with respect to that state. So if we consider that the basin stability 1 means all the initial conditions are going to the synchronization state. And when we plot this basin stability as a function of the noise strength, you can see that there is a peak around this some transition value of D, and then there's a drop. So what happens is there's a very small window of the noise strength where you get the basin stability 1, and all the initial conditions are synchronized. Otherwise, they are going to be unbounded. So there is a limitation of this noise-induced synchronization. Okay, so you can see that very small range you are getting this synchronization. So so what we have done is we have considered this noise only in a certain state space. So we have modified this the noise term by this introducing the another factor alpha x, where alpha x takes the value 1 if you are in a certain state space. Say x is the state of the system, and C the center of the attractor. And if you define some the radius where which is the kind of the noise active range, and in that range only you will have a noise is added to the system, otherwise not. So it is like visible range of the noise which is effective to the system. So this is the modification, and with this you can see that you can look at this as a time series where you can see this alpha, which is this takes the value 1 and 0. You can see that this is going on and off, and the average synchronization error, if you plot as a function of the noise strength for different values of R, here with the dark black line, which is R infinity, I have considered as there is the noise is applied in the entire state space, which is the normal case which you have considered in the past. And otherwise, we can reduce it to the 60% or 80% of the attractor size, and that is the state which is experiencing the noise. And with this, you can see that we can achieve this the synchronization at the smaller noise strength also. And we have plotted this the basin stability also, and here we have observed very interesting results that the basin stability, which was going a sharp peak around this transition from no synchronization to synchronization around D equal to 30, we get the extended flat range of this basin stability 1 for different R values, which is the noise range. And here is in the 3D plot of the this basin stability in R and D. So this is the what we have observed, and then we have also look at the average time spent by the trajectory in the contraction region. So we have plotted the contraction region of the attractor, the synchronization manifold, and then you can see that the blue attractor spends the more time in this contraction region as compared to the uncontrolled one. Now, when you look at this, the time spent in the contraction region for different cases, you can see that for the normal case when there is no restriction on noise, it increases and then start dropping after certain noise strength around 40. But in the case of the constrained noise, it is continuously increasing. So because of the constrained noise, we are able to confine the attractor in the contraction region, and that is the main cause for the synchronization with the larger basin stability in the extended region. We have also calculated the transverse Lyapunov exponent and the entropy, and we have also checked the results for PR circuit model. HR neuron case also we got the similar results, and with this I can conclude that the intermittent noise enhances the synchronization. So that was the main observation, that if you somehow can restrict the noise, then you can get the synchronization for the lower noise strength as well as with the larger basin stability. So with this noise, we have also tried for the multi-stable system to control. Can we control the multi-stable system with the intermittent noise? So multi-stability here, I means that the depending upon the initial condition, system can go to 2 or more different states. So you have various different examples here, and then you can classify the control of multi-stability into non-feedback, feedback, and stochastic control mechanisms. So sometimes, because depending upon your initial condition, your asymptotic state may be A or B, so you don't want to have an uncertainty in the final state of the system. You want to have only one fixed state of the system. So for that purpose, the control is very much required, and there are various methods proposed in the literature with a non-feedback control, with the short pulses, parametric forcing. In the feedback, there is a linear, periodic, and delayed feedback systems. There is stochastic control, unrestricted noise control, noise burst, stochastic resonance, and so on. So there are many examples. But when we have looked at the unrestricted noise stochastic control, we found that there is a continuous attractor hopping. That means that when we introduce the noise, then the attractor, we are not able to stabilize the attractor to one particular state. So there is a keep on hopping between the attractor 1 and 2. So when we consider this, the intermittent noise in this form to the this bistable or multi-stable system, so we have added this noise with epsilon h of x a eta t, and h of x is this the function which is a spatial control function, whether you are in a certain state space or outside that. So this was applied to the inversion invariant bistable system, and this is the system, and it shows this these two attractors A1 and A2 depending upon the initial conditions. And this is the basin of these two attractors. When we apply the noise, and noise can be in the space. So if you are applying the noise in this particular strip form, then it can be from between -2 to +2. So anywhere. So if we apply the noise around this attractor A1, then you can see that you get the final state, which is A2 only. And here we have plotted this basin stability, and you can see that initially it is 0.5 for both the attractors. So that means that half of the initial conditions are going to the attractor 1 and other half are going to attractor 2. Now when you introduce this intermittent noise, you can see that this goes to the one of the attractor and not to the other one. So this, so this is the basin stability of the attractor 2, which goes from 0.5 to 1 in this case. And here you can see that the trajectory of this attractor is shown, which is switching from this state to the another state here. And this is the basin stability. And the rho is the kind of the range where the noise is applied. And the interesting thing here, which is to be noted, that in the case of the unrestricted noise, when there is no restriction on the noise, this because of the attractor hopping, the basin stability cannot be this from going from 0.5 to 1. It is always going to the 0 in both the cases, because we are not able to count the or identify the final state of the system. So that is one difference from the unrestricted noise. So we have considered another examples like Duffing oscillator also. This scheme works. And we have also tried for the logic gate operations, and we could do it successfully for NAND and NOR gate, where we apply this intermittent noise, and we can see that these are the results. We have also checked for the toy model of this tri-stable state. There you have 3 stable states, and you are able to achieve the this control of the annihilation of the one of the attractor by removing this one of the attractors here. So that you can do. We have also done with the 3 attractors, 2 periodic and 1 chaotic with this basin, and we can see that we could target the one of the attractor by almost removing the other 2 attractors. So here the final the conclusion is that the intermittent noise can also be used to control the multi-stability in the system as compared to the unrestricted noise, where there is a continuous attractor hopping. Here we are able to stabilize the attractor to one of the target state. So with this, I would like to conclude this talk. And there are 3 main components. We have discussed that intermittent interaction leads to the first order transition from oscillator to steady state, and this shows more complex behavior with bistable small and large oscillations, coexistence of oscillatory and steady states. And the intermittent noise help us to enhance the synchronization with the spend of more time in the contraction region and wider noise intensity range with the amplified basin stability. The last one which we have discussed is the control of the multi-stability with the intermittent noise by annihilating the undesired effectors. So with this, I thank you, and I'm open for discussion.
Yeah. Thank you, Manish. So now the session is open for questions, clarifications.
Manish, how do you introduce intermittent noise, state-dependent intermittent noise in a practical way? An actual system, how do you hope to introduce this state-dependent intermittent noise? Because the noise arises naturally in a system at a certain strength. And how do you expect that you can restrict this to a specific region of the state space?
Yes. Yeah, that is interesting and important question, because we here it is kind of another putting the control mechanism to restrict the noise. So if the noise is there in the space, and it is like the state space which can observe the noise, that we can it is like the noise free region, or the region where you have the noise. That is, either then you apply the noise in that particular region, or you restrict the switch off the you have to filter the noise from the rest of the region.
Yeah, I have a difficulty. I mean, noise arises naturally in a physical system.
Yes.
And how do you associate that with the specific value of the state variable? So it's a little bit difficult to imagine, but I do hope there are ways to.
Yeah, inherent, but external noise. So here I was talking about the external noise only.
Yeah, but noise essentially means it could be intrinsic or external. Okay. So, for example, in the logic gates and all you talked about.
Yes.
So you normally talk about the intrinsic noise that arises in the circuit. So how do you control that? So I think one has to think about practical ways.
Practically, yeah, it is it's more challenging, and it is important also, because if you can you have to filter out the noise. So this noise filtering has to be. So I'll think about that.
Yeah. Okay.
So any other questions? You have, yeah.
Hi.
Yeah, you can raise your question. No, we are not able to hear you. We are not able to hear you.
Just 1 minute. Now it's fine?
Yeah. Now, yes.
Yes. Manish, I joined your lecture just after 30 minutes. Yeah. Just I listen your lecture, intermittent noise. Yeah, just I am talking just usually the noise always in and synchrony. If we have two couple oscillators, and if we add noise, additive noise, then always synchronization will occur. So is there any difference between your intermittency noise and your full noise, that is the noise will present all times? Have you checked, or have you difference between these two noise? What will happen? Enhancing will be more, or enhancing will be same?
For the unrestricted continuous attractor hopping, and you are talking about the energy.
No, energy, no, not synchronize.
Synchronization
Just two couple oscillators couple each other, and if we add additive noise on both the oscillators, then enhancing synchrony will occur usually.
So I have checked that when you have an unrestricted noise,
Yes.
then there is a synchronization, but the basin stability is, I'll show you the figure. Yeah, you can see this.
Yes, yes.
So if you look at the black curve,
Yes.
the first one, which and
Uh,
this is the basin stability, and basin stability is maximum 1 around d equal to 30, which is the transition point from no synchronization to synchronization, and this is for unrestricted noise. But and after that, system goes unbounded, and most of the initial conditions are not synchronized, and the basin stability is small. But when you consider the restricted noise, this basin stability region is increased,
yes.
and you have a larger noise density where you can achieve the synchronization. So there is a huge difference.
Yes, yes, yes. This is one of the positive results.
So what is the meaning of increasing the strength to 200, 300 units? Manish?
Sorry, sir?
In the figure, in the previous figure you showed, 200, 300 units and so on. So with that kind of strength, essentially you are destroying the system, original system.
Yes.
Will be the original system because its strength is very high.
Yes.
I don't know. Prabhakar, you have any comments?
Yeah. So this you can still have a synchronization for larger noise density, which is relatively very high. It may destroy the attractor, but if you look at there is a distortion in the attractor. But if you look at the uh, this case, so if I just compare this case, this is the unrestricted noise. So
Yeah.
achieve the synchronization at d equal to 30. But when you
Yeah.
restrict the noise, you can achieve at the lower values, 20.
Okay.
So that is one difference. Another difference is the basin stability. Basin stability is taking its peak value around 1 for very small range, and it is higher. So you are right that 100, 200 noise strength is not required, and it will definitely destroy the attractor. But we are able to achieve for the lower noise strength also.
Okay.
And that figure is just for the to show the stability of the basin for the larger noise strength, which is practically not required.
Okay.
So this is the figure for the unrestricted noise.
Any other question?
There is one in Dropbox.
So, Manish, there is a question in the chat box.
Yeah, more or less it is same. Basically, the key mechanism, if I just tell you this part, yeah. As long as you are restricting your this trajectory in the contraction region, so that is the key mechanism. So by restricting noise, you are able to maintain the oscillations around the contraction region, so that you are able to achieve the synchronization earlier and for larger initial conditions. For all different distributions.
So this is that clear? Yes. So any other clarifications? So, so we are not getting any questions. So, so since I'm not getting any questions, I would like to conclude the session by thanking Dr. Professor Manish Shrimali for giving a very wonderful lecture. Okay, for accepting our talk and giving a very wonderful lecture here. Thank you, sir. Thank you very much. So, if students have some doubts, they will write to you, sir.
Sure, anytime. All the students are welcome. They can just drop me a mail, and I'll be very happy for that. And happy to see Diwakar also by the end, because he recently wrote the nice review report on the time varying interaction. So that will help the student to read more about this.
He just arrived 10 minutes back, Department of Non-Linear Dynamics.
Yes.
He's
Manish, I am here at Bhadi also.
Okay.
Yeah,
Great.
just came after about 10 minutes.
Okay, thank you, ma'am.
Thank you, Lakshman sir, and thank you, Santil.
Okay, bye.
Bye.